If you've spent any time on the internet looking up how to build something, you've seen the claims. This joint is unbreakable. This is the glue pros swear by. Follow this one simple trick for a bond stronger than the wood itself. It seems like every forum, every video, every blog post has its own secret sauce for creating something that will last forever. But here's the thing, everyone's got an opinion, but very few people have data. And as an engineer, opinions without data are just, well, they're just like, no see. I'm tired of the noise. So today, we're not trusting anyone's word for it. We're going to put these claims to the ultimate test. We're going to use science to settle the score once and for all. I went through and found the 7 most common woodworking myths, the things you hear over and over again, and decided to put them head to head in a battle of pure, unadulterated strength. It's not about which one looks the strongest or which one has the most hype. It's about which one can actually take the most punishment before it gives up. The plan was simple: build 7 identical test pieces, each one using one of these legendary myths. We'd use the same wood, the same dimensions, and the same level of care for each one. Then, we'd rig them up to my custom-built stress testing machine and apply force until something snapped, shattered, or just plain fell apart. We're going to measure the exact force required to cause failure, and find out which of these myths are legit and which are just, well, myths. And I'll give you a little spoiler. One of them didn't even make it to the testing rig. It failed instantly. Let's get into it. Okay, let's start with the big one, the phrase you hear everywhere. The glue joint is stronger than the wood itself. It's the holy grail of woodworking, right? The idea is that if you do it correctly, the wood fibers will tear apart before the glue ever gives way. So, I took 2 pieces of clean, freshly cut pine, applied a generous layer of a popular wood glue, clamped them together with just the right pressure, and let them cure for a full 24 hours. The prep was, by all accounts, perfect. This should be the textbook example of a perfect glue bond. When we put it in the testing rig, the results were fascinating. As we slowly ramped up the pressure, you could hear the wood start to creak and groan. And then, with a loud crack, it failed. But here's the key detail. The break wasn't a clean snap along the glue line. Instead, huge chunks of wood fibers were ripped out from both sides, still firmly attached to the glue. The myth is technically true, but with a huge asterisk. It only holds up if your surface prep is absolutely flawless. Any dust, any oil from your fingers, or any uneven clamping pressure, and the glue itself becomes the weak point, not the wood. So, yes, it can be stronger than wood, but only under lab-perfect conditions. This one just feels intuitive, doesn't it? If 1 screw is strong, then 10 screws must be 10 times stronger. It's the brute force approach to building. To test this, I built 2 identical lap joints. For the first one, I used just 4 screws, placed strategically at the corners to distribute the load. For the second one, I went all out. I packed in 12 screws, creating what looked like a metal-studded fortress of a joint. It definitely looked more robust and felt heavier. In my head, I was already picturing it putting up a monster fight in the testing rig. But when we started applying the load, something unexpected happened, and it happened fast. The joint with only 4 screws began to deform slowly, the wood bending and the screws pulling under the strain. It put up a respectable fight before the wood finally started to split. Then we tested the 12-screw version. Almost immediately, with far less force applied, a crack appeared. The sheer number of screws had created so many holes and stress points in a small area that the wood had no integrity left. It acted like a perforated line, and the joint didn't bend. It just snapped clean off. More screws didn't add strength, they just gave the wood more places to fail. Pocket holes have taken the DIY world by storm. They're fast, they're easy, and they promise a strong joint without any of the complicated cuts of traditional joinery. The marketing tells you they're just as good as the old ways, but just faster. So, I built a classic T-joint using a pocket hole jig and the specialized screws that come with it. For comparison, we'll see how it stacks up against a traditional joint later. The assembly was incredibly quick. A few minutes to drill the holes and drive the screws, and it was done. On the surface it looked solid, but the test tells the real story. Under a light load it held up just fine. This is why it's so popular for building things like face frames and simple cabinets. In those applications, the stress is minimal. But we're not here for minimal stress. As we cranked up the force, the weakness of the design became glaringly obvious. All the force is concentrated on the small threads of the screws, digging into the end grain of the wood. There was no groaning, no bending, just a sudden, catastrophic failure as the screws ripped right out of the wood, taking chunks with them. It's a great shortcut for light-duty work, but it's no replacement for a well-designed traditional joint when real strength is on the line. So, epoxy is often called the superhero of adhesives. Got a crack? Well, just fill it with epoxy. A rotten spot. Dig it out and, pack it with epoxy. It's often touted as this miracle cure that can make any broken piece of wood stronger than it was before. To really put this to the test, I took a piece of wood, deliberately snapped it in half, and then, meticulously glued it back together with a high-strength 2-part epoxy. I filled the entire crack, clamped it, and let it cure into this solid, plastic-like seam. Honestly, it looked and felt incredibly rigid, but putting it to the test was a real eye-opener. The epoxy itself is insanely strong. That part of the myth is absolutely true. As we applied pressure, the epoxy seam didn't even flinch. It was completely unfazed, but the wood around the epoxy, that was a different story. Because the epoxy creates an area of extreme rigidity, all the stress from the bending force was transferred directly to the wood right at the edge of the repair. Instead of the force being distributed across the wood, it was focused on one tiny line, and with a sharp snap, the wood broke again, not at the repair, but right next to it. The epoxy held, but, well, it made the surrounding area so brittle that the wood itself became the point of failure. Alright, so plywood is an engineering marvel. By layering thin sheets of wood, or plies, with the grain alternating at 90-degree angles, you create a panel that's incredibly stable and resistant to warping. It's known for its uniform strength, and honestly, that leads a lot of folks to believe it's superior to solid wood in every situation. So, I cut a test piece from a high-quality sheet of 3/4-inch birch plywood, ready to see it outperform a regular pine board of the same size. The thinking here is that the cross-laminated layers will prevent the kind of splitting we usually see in solid wood, and when we tested it by applying force to its face, the plywood was an absolute beast. It bent and flexed, distributing the load across its entire structure way better than solid wood. It took a massive amount of force before it finally started to fail. But, and this is a big but, that strength only exists in one direction. We then ran a second test, this time applying force to the edge of the plywood, trying to split the layers apart. It was a completely different story. With very little pressure, the glue between the layers just gave way, and the plies started to delaminate and peel apart like an onion. So, plywood is incredibly strong across its face, but its Achilles heel is definitely its edge. This is, honestly, one of the most deep-seated beliefs out there. If you want it to be strong, build it out of hardwood. Oak, maple, walnut, these are the heavyweights, while softwoods like pine are seen as the lightweights, only good for simple projects. To challenge this idea, I prepared 2 test pieces. The first was a piece of beautiful, dense oak, a classic hardwood. The second was a humble piece of pine, a softwood. But here's the trick. I cut the oak so the force would be applied against its weaker grain direction, while the pine was cut perfectly, with its grain aligned to provide maximum resistance. The results completely flipped the script on what we think we know about wood. We tested the mighty oak first. Because the force was working against its grain structure, it split relatively easily, shearing along the grain lines with a disappointing crack. It was strong, sure, but not nearly as strong as its reputation suggested. Then came the pine. Lined up perfectly with its grain, it was able to resist the force for much, much longer. It bent and compressed, using its fibrous structure to its full advantage. The weaker softwood, when used correctly, dramatically outperformed the stronger hardwood that was used incorrectly. So it's not just about the type of wood, it's about understanding and respecting the grain. Finally, we come to the methods that have been around for centuries, long before fancy glues and power tools, traditional joinery. For this test, I crafted a mortise and tenon joint. This involves cutting a slot, the mortise, into one piece of wood and a corresponding tongue, the tenon, on another. The pieces interlock perfectly. There are no screws, and while glue is often used, The strength comes from the geometry of the wood itself. This is the kind of joint you'd find in a 200-year-old barn or a piece of fine furniture. It's time-consuming to make, but the legend says it's indestructible. And honestly, this was the champion of the day, and it wasn't even close. When we started applying force, the entire assembly began to bend as one unit. The joint transferred the stress seamlessly from one board to the other. It groaned, it creaked, and the wood fibers began to compress and tear, but the joint itself just would not let go. Unlike the pocket hole that failed suddenly or the screws that split the wood, the mortise and tenon failed gracefully. It gave plenty of warning and held on until the wood around it was completely destroyed. It really proved that the old masters knew what they were doing. Smart geometry and an understanding of wood mechanics will beat brute force every single time. So after all the snaps, cracks, and catastrophic failures, what did we actually learn? We learned that there are no magic bullets. There's no single glue, screw, or method that's universally the best. The real secret, the thing that separates the projects that last for generations from the ones that fall apart next year, is understanding why things work. It's knowing that glue needs a perfect surface, that too many screws create weakness, and that the direction of the wood grain is more important than the wood's name. It's about choosing the right technique for the right job. The mortise and tenon won today, not because it's old, but because it's smart. It works with the wood, not against it, and that's the biggest takeaway here. Your goal shouldn't be to find a way to brute force a joint together. It should be to understand the forces at play and design a solution that handles them elegantly. I hope seeing these myths get busted helps you do just that. Because if this video saved you from building a bookshelf that would have collapsed or a table that would have wobbled itself to death, then you already won today. You've gained the knowledge to build better, stronger, and smarter. And that's what this is all about for me. Using a bit of science and engineering to peel back the curtain and understand the world a little better. It's way more satisfying to build something knowing it's strong because you designed it to be, not just because you hoped it would be. So next time you see a claim that sounds too good to be true, be skeptical. Ask why, and if you can, test it. Because building something with your own hands is great, but building something with your own mind is even better. Thanks for watching, and I'll see you in the next one.